So he quickly wrote the 64K framework, and it's, even though it was very simple in what it did, it was very effective. So the idea was we basically make a couple of 4Ks and glue them together. What we were good at the time was to make ray marching 64K. So we have a single full screen polygon that is being passed to a shader, and the shader decides what's happening in every pixel, and it's ray marching and colorful stuff comes out, which is what a lot of 4Ks do, and which was what we were doing, and we decided to make a bunch of these and chain them next to each other. And you can see in the screenshot at the bottom there's these blue bars. That is a timeline where you can arrange which shader gets rendered into which buffer at what point. And then there's the output and some parameter editor and so on. And it also, since this has multiple bars, you can choose from multiple frame buffer objects which renders where, so you can do a little bit of post-processing. It was all quite rudimentary, but it worked, and a colorful demo came out with a very trancy soundtrack and lots of strobo and dancing gummy bears. But the thing that I found most important here was that this tool, maybe I can go back to the screenshot, has this spline control. So to the left of the screenshot you see there's some parameter that is animated over time. And the first lesson that I learned in making this was actually the first 64K I made. So the lesson I learned is that if you're used to making 4K, 64Ks are so nice. Because, as I'll mention a little bit later in the talk, if you know how to do one 4K and then you add a second one to it, then suddenly the second one doesn't really need that much additional space, and you can add another one, and suddenly you just have lots of content in the 64K, and it's easy to fit it in 64K. So if you just have a shader toy multiplexer, that totally works as a demo tool. Shader toy, if you don't know it, is this website where you can build shaders that operate on full screen polygons and that just do something, and some of them are quite fancy, and if you just take a bunch of toy shaders and multiplex them in time and then maybe control some parameters, then you have a 64K capable demo tool. And there are some surprisingly prolific groups that do exactly that. The Hackers demo tool, which I've not used but I've seen, you can copy paste stuff from Shader Toy and then have a file where you say a timestamp and a value for all parameters. And that's it. They use nothing else. All the demos you've seen from them exactly contain only that, which I find shocking because it's impossible to tune proper colors and camera paths and so on, but they can do it, so I'm quite impressed. Yeah, and that's exactly the next point. Choosing good colors and animating things to look good is a pain if all you do is write a shader file. So if you just have a text file in front of you, giving you RGB values for red, green, and blue, and you are supposed to choose colors that look good, it will inevitably look like codec colors. So it will necessarily look ugly. And we were working for a long time for a solution to that. So we wanted our own demo tool then, because Pascal is not exactly a language that anybody in Mercury uses or likes. And the problem was that we were lazy. So writing a demo tool requires you to write a user interface. As rudimentary as you might want it to be, you have to write a user interface, and it's always horrible. So you try to avoid that as much as you can. And then we discovered this tool called AntTweakbar. AntTweakbar is a library that you can, if you have some OpenGL program that runs, you can call a couple of library calls to tell it, these are some variables I have, open me a window, and you can tweak them around. Literally does what the name implies. You give it some variables, and you can tweak them. And as you can see in the screenshot, there's some windows that pop up, and you can tweak colors and parameters and so on. And it's great. It's unfortunately not possible to animate anything with it, because all you give it is a memory location, write your float value or write your color here, and you can tweak it and you can wobble around with it, but you cannot animate it, and there's no format to save it. And if you want to do that, you have to build it on top of it, which unfortunately we did. For revision 2012, DFox asked us to create the invitation about, I think, 2 months before it was supposed to be released at TUM, which is always the time when the revision invitation is coming out. And we had nothing except AntTweakbar. And we just decided, OK, everything we do in our demo is animated by splines. And keyframes, every keyframe has an AntTweakbar panel, and then the panels were popping up all over the place. And the user interface was horrible. This is a screenshot from way further down the line, I think 2 years later. The first prototype of the city in the Timeless was also still animated, or not animated, but tweaked with untweaked. But as you can see, it looked a lot different later on, but this was an early test for that. So Epsilon was our first own 64K, and that it was a framework we had written ourselves based on untweakbar. We didn't really know what we were doing, except we wanted to make things small, and somebody said that bytecode interpreters are a good thing to make things small. So we had actually 3 different ones. One for the synth, one for building parameters up, and one for writing text overlays. And they didn't know of each other, and different people wrote different parts of the code, and was quite bad. The tool crashed all the time. For example, if the keyframes, every keyframe popped up one of these windows. If you wanted them to move them around in time, you had to tune a floating point number, which gave you the time. And if you moved one over the other and the difference was 0, it crashed. So you could not do that, and there was no copy paste and all that. It was clumsy to the extreme, and it was also basically we only started animating stuff with it, so using it properly at the party place. But the good thing it did, and the one thing that untweakbar does really, really well, is if you have a color that you want to edit, it has a really, really nice color editor. So you can switch between, I want to select RGB or HSV or different color spaces, and you can drag around and tune them fine or coarse. And Psychon, our Swiss graphician, was finally able to tweak colors, which he had not been able to do before. So suddenly our demo started to look good. Suddenly we had colors that no longer are coder colors. Everything before was colors we were choosing as numbers in a text file. And suddenly we had good-looking numbers. Which brings us to lesson number 2. Use the right control elements in your graphic user interface. If you want to create anything that looks good, this is not just a lesson for 64K, for any kind of demo, intro, or whatever. If you only write numbers in your code, you will never have good-looking colors. If you hand code camera paths, you will never have believable-looking camera motion. I mean, if you want to have something circling around a point, you can still use sine and cosine, but anything more complex than that, you're going to have either an incredibly long and hard time suffering a lot, tweaking this, or or you need to have a better tool. So the important thing to keep in mind, and that's the philosophy in all of our 64Ks, is that a parameter, like a floating point number that you use anywhere, is never just a floating point number, it always has a meaning. And that's literally called a meaning in our code base. It can be color, can be an angle, position, a speed, a fraction, an integer, and so on. And whatever this meaning that's assigned to it is, chooses what the appropriate control element is. So this is a screenshot from our AMBOSS 64K tool, and you can see there's a number of parameters, and the first one is the color, so it gets a color selector, and the second one then, I think the next 2 are angles, so it's a floating element, but it tweaks very finely, and then there's stuff like strength, is a number, a number on the range of 1,000, so it has a control element that just scales much more strongly, and so on. Drunk usability is also important. That, of course, depends on your working style. But we have this tradition of finishing stuff at the party, which mostly means starting stuff at the party. So code is there, but no parameters are chosen, and nothing is time sequence or anything. So we start, and then it just happens that beer occurs, and suddenly it becomes important that the tool still remains usable while drunk. So there are some fundamental design decisions that have to go into that. For example, if you can click somewhere to destroy something, it is always good to be able to restore it by clicking the same space, because everything else doesn't work when you're drunk. Also, user interface elements need to light up when you hover over them, because if you don't see your mouse cursor, it's bad otherwise. Okay, and then we restarted from scratch, because after Epsilon, we had a bit of disagreement how a demo group should be run and what we should be doing, and some people didn't talk to other people anymore, and some people left. And especially one member required that we no longer look at the Epsilon code base, and we deleted it all, and we started over, which in retrospect was very good, because if we had tried to get this horrible mess of an untweakbar syncer working, it would have probably been more work. Oh, a new message from assembly organizing. Wonderful. Would have probably been more work than writing it from scratch. For the first 2 years, nothing happened because the problem seemed too large. Where do we start with writing a 64K tool it seemed just like too big of a problem. And then in the meantime, we did some demos with other people like Mirage, Topi and me. We did a demo for Payback here in Helsinki in 2014 on a weird Chinese emulator console, like a handheld ARM or MIPS-based thing, which again involved me writing color values into a header file with a text editor. And I swore never to do that again, which so far has actually worked. And I decided that the 64K tool ain't gonna write itself, so I started with something. And I started once again with what we did basically from the start by chaining 4K or chaining four small full screen shaders next to each other. The first thing that I wanted to do is not even tune parameters or anything. All I wanted to do is I have a timeline, a graphical user interface where I can arrange which shader gets rendered when, and I wanted this to be my own code that I understand. And I wrote this. This silly window was the very first version of the AMBOSS demo, what later should be called the AMBOSS demo tool, and some of that code survives in it. At the bottom you see these orange chunks are just the different shaders, and they're arranged in a linear timeline, can be dragged back and forth. And at the top it renders something, it was horribly unusable. And it also had the problem that if all you have a timeline, if all you have is a timeline, then every problem looks like you have to beat sync something. That is how this group got its reputation. So that happened, and the timeline itself was actually very nice, and it allowed random soundtracks to be synced with random shaders. And then that tool evolved, because as soon as the timeline was there, it was more or less trivial to add also 1 or 2 parameters to be tuned by that. And then we got the idea, well, if all we're doing is ray marching, and we're good at ray marching, we just want to render full screen shaders that feed into other full screen shaders for post-processing and eventually end up on the screen. Why don't we build a tool that does exactly that and nothing else? Which then in the most recent version, this is the Fermi paradox state of that tool. You still have the timeline in the bottom left, and you have the parameter editors, and you have other stuff flying around, but fundamentally it is still doing exactly that. And the central feature is that shader uniforms, so in the shader source code, any uniform parameter that has a meaning comment to it becomes an animatable parameter. So it looks like something like this. You have, for example, a uniform angle, and we have meaning angle, so it knows what control to render for it, or you have a color, and that has meaning color behind it. And it parses these comments from the shaders and automatically creates the parameters in the tool, and then they're animatable, and that's what happens. And all of these then can be given keyframes in the time frame, in the timeline, and interpolated given a number of splines. And normally, if you have a parameter in your shader, you set it once and you never set it again. So it's a floating point number that you store somewhere, and that is not big, and you can just do that. And even if you have the most complex camera path that you ever want to store, a camera consists of 6 vectors, or 6 floating point values, and maybe 20 keyframes that you have. So, you know, you can store 180 floating point values in 64K without a problem. So that is all our demo tool does. The demo tool does not actually know what it is rendering. It just knows that there's a shader feeding into another shader, until it didn't anymore. But first, a small excursion about how do we get this to be small enough. All we have are shaders and some numbers. So we have source code, shader source code, that gets processed, and some numbers from the timeline. That's time positions and then values of anything. Nothing else. To get them as small as possible, it's always important to make the data as regular as possible. So you want the data not to look like random noise, you want the data to look as regular as possible. Because if you think about what a compressor does, even though they work in very different levels, it's always good to have in the back of your head, if you have the same thing multiple times in a row, the compressor does good things with it. So if, for example, anywhere in your data, you have 5 times the same object, a compressor can replace it by 5 times this object. But if you have something like, you know, 2 gray ones, 1 red one, 1 gray one, the compressor has no choice but to replace it by something like 2 gray ones, 1 red one, 2 gray ones. So that is going to be larger in the end. So if you can reorder your data in some way, you might want to get this red box at the beginning or the end. and make sure that all the similar things are grouped together. So this means for the shaders that you want to make sure that your shaders look as similar as possible. Everything is a remix. That is especially true for shaders. I mean, when we write 3 different effects, 99% of the source code looks identical, and there's some numbers tuned and maybe a couple of lines and a couple of functions. And then why not put them just next to each other in the file? One problem, or one tool that a lot of people use to make their intro small is the shader minifier by LLB, which is an excellent tool which makes shaders quite small. Especially it takes all the identifiers, all the names you use, and crunches them to as small a size as possible. So maybe A or B can be a name. But if you do this for each of your shader files individually, the names will be different in each. If you have 3 ray marching shaders, all of which are 1,000 lines long, and all of which use the same ray marching loop but differ in one function, then they will not look identical. So what we instead do is we globally replace the identifiers so that the marching loop and all the big parts of shaders that are commonly used still look identical, and then we pack them next to each other. So we make sure that they are semantically grouped, that we have the ray marching shaders together, the post-processing shaders together, and whatever else we might be doing. So that shaders that look the same are together, and then they just pack really well. Adding an additional space scene in the Fermi paradox, which actually has 3 different times the same scene with slightly different planets. Adding each additional one only took 200 bytes more. So it was okay. And then you have to do the same for your data. Splines and parameters, times and values are basically what you have lying around. And you again want to make sure that the data you store is as regular as possible. So you want to pack similar data together. And what we do is, in our source code, we have a bunch of bytes, a bunch of ints, and a bunch of floats. These are the 3 data structures. Or by now it has also gotten a long int thing. But the 4 arrays, all data that we need in the demo is passed in these 4 arrays. And they're literally called, I think I've got a screenshot here, I'm not sure if that's readable. They're called sync data ints, sync data long ints, sync data floats, and sync data bytes. And they are not structured in any way. And there's no data structure definition. In export, the code just pushes all the bytes it needs in there. And then when regenerating, it transforms them back again. So if you look at, for example, the ints, the first of these arrays, it starts with the numbers 1280 and 540. That is the screen resolution. And then following that, there's, I think, the number of scenes in the demo and so on. And then it accesses all the other data as it reloads it. So in the intro mode, what runs when you see the loading bar, it's actually just taking data in exactly the same reverse order as it put it in before from these arrays and do some transformation on them. If, for example, you have positions, you might want to delta encode them, because if you have stuff at regular intervals, then you always have the same delta, and that compresses well. Or other transformations that might be nice, depending on what it is. And that's where the meaning comes in, because suddenly it's not just nice to select the correct user interface by saying this is an angle, this is a color, this is a position, but it also becomes very useful for compressing, because if your scene is maybe, I mean, logically 2 by 2 meters large, the numbers, your coordinates that you have are always going to be in this range. Whereas your colors might have different values and your angles might have different values, so it makes sense to have all positions grouped together. And that exactly is what we're using here when exporting these sync data values. We are giving all positions into the float array, and the next after that there's going to be all colors, and then it's going to be all angles and so on. Semantically grouping stuff allows the compressor to just compress similar things together, and especially if your demo is quite regular and everything happens at regular intervals or so on, or in other words, you're doing a techno demo, then this compresses really well. I also recommend you, if you're interested in this, to see Ruk's wonderful working with compression talk, where he goes into way, way more detail than I could go into 2 slides here, where he gives lots of practical examples on how to compress things and why they had so much space left over in the product. And now this slide might confuse you. Code is actually bad. If you want to get your binary as small as possible, or you want to have more space in the 64K, remember that shaders pack well, since they're text, source code text mostly. Data also packs very well if you format it properly, but code doesn't. Even though we have executable compressors like KCrunchy, which do very advanced transformations on your code to make sure that it can be fed to a compressor quite nicely, the compiler itself is still very dumb with producing your code. If you want to set up a list of your shaders, if you want a list of whatever you have, like the possible scenes in your demo, the post-proc paths and so on, you can do that with code. You can write a function at post-proc path and then call that 15 times for all your passes, and that works. But that will cause the compiler to create something like, I put data on the stack and I call a function and there's a return value and all that. You don't really need that if alternatively you can specify the same in sort of data. So quite concretely, I would say don't write a for loop to generate the numbers 1, 2, 3, 4, 5, 6, 7, 8. Because if you just write this into your integer array, the compressor sees, oh, subsequent numbers. Yes, compress that away. And that actually goes quite counter to what most people will tell you about making size-limited productions, in that you don't store any data. You always generate everything because that's smaller. And that is true for a lot of things. But you also have to keep in mind that there are things you better do with data than with code. And our demo tool that was designed to render full screen shaders into full screen shaders, already at the second release we did with that, was completely particle based, because we were doing Luma and it only had particles. And then we added polygon height field rendering, and then we added volume rendering, and then we added compute shaders. And in the end, in Fermi Paradox, we have 4 rendering methods rendering every frame into the same buffers at the same time. And if you look at this, is an excerpt, a small part, like 1/10 of the source code file of Fermi Paradox that sets up the render passes and how they connect to each other. This is basically a node system, except we do not have a graphical interface saying what renders where, and there's just code, and I don't know if you can read this, is basically creates passes and connects them to each other. So for each of these calls, connecting a pass to one another, which is basically just saying this number to this number and that number to that number, the compiler has to create the function call and has to find the variables from somewhere, and then they are in a singleton object, so it has to maybe call a constructor or something like that. And it just isn't very good to do this in code. Which is why we once again, after Fermi Paradox, threw our tool away and wrote a new one. That one is now called HYDRAZINE, and suddenly everything we do is data. This is what a visualization or the actual working environment looks like. Fizzer of EOS said that our tool looks like the schematic diagram of a cow's intestinal tract, which is part 32. And all this setting up of render passes and connecting stuff, and also what animates how, is no longer handled in code, no longer explicitly specified. What you can see in here is you have this thing up here, which is the timeline. It gets fed the time from this node, and then it connects to all the parameters we would like to animate. Here we have, for example, color for a couple of font renderings. Here we have the camera, and then we have sun position and things and so on. The idea is that in this node system, we only store this rendering process transports its output there or its output there. And we ignore all sorts of data types. We have one data type that is a 32-bit memory value, and it contains either a floating point number or a texture ID or other GLUINs or something. And the editor, so the toolkit, knows what types can be connected to which. So for example, all the green lines are floating point parameters, and all the orange lines are textures being transported. And then I think there's also purple lines, which are image objects and so on. But the intro code doesn't know about that. The intro code only knows node 3, exit 5 to node 5, input 3, and nothing else gets stored. And then if you've worked with node systems before, there's always some of them work horizontally and some of them work vertically, and some people fight about which is better, and we actually have both types of connectors. The connectors that you see that are going top to bottom, like in the timeline node, up here, there's time coming out of this timer, and it goes into the node. So it gets produced, and then it gets consumed, and that's it. And most of the textures here get produced, and then they get consumed, and that's it. But then there's also buffers that are being rendered on, and there's side effects happening. And we thought, why not represent side effects as sideways connections? So all these horizontal things you see here, there's a buffer being created, it's being cleared, something renders into it, a texture gets extracted. Or here, buffer gets created, cleared, one thing renders into it, another thing renders into it, a couple of textures get extracted, and then it gets processed further onwards. So we now have this way of specifying what happens in our demo from, or in our intro, from version to version. It can be entirely different. We are no longer constrained to doing full screen shader quads. We just do whatever we like. And most of the time it's very horrible, but in the end sometimes it works really well. Yes, and there's especially no more code specifying connectivity. We recreated the Fermi paradox, basically the rendering pipeline of Fermi paradox in this tool, and we saved about 10 kilobytes just by not having code do it, but having this data do it. And suddenly it gets hard to fill 64 kilobyte. Before, we sometimes reached the 64 kilobyte limit, but it was never a big problem. In the 64K compo here, I will have a entry, might have an entry that still contains the entire 64K compo entry from revision, because I didn't have to take it out, because there was enough space. Okay, other miscellaneous hints from the 64 kilobyte front that we found are important. One important thing to structure the team is to make all interfaces usable by a drunk revision. As a coder, you can test that yourself by getting yourself drunk and then stumbling to your room and looking at your computer for 2 seconds. If you notice, if you understand what you're doing, then it would also be usable by your drunk revision. It is important to misunderstand code. And that is something that works surprisingly well for us. In a piece of code that Cooper wrote or Lars wrote and that I'm looking at and not really understanding what it does, and then just trying to make it look good, it very often happens that afterwards they say, this was not supposed to be like this anyway, but it looks so good. And it happens in all three directions that, well, somebody wrote code, somebody else misunderstood it, and then it got adopted back because it's better, or it became something entirely different. And it's very important to take code, not comment it, and misunderstand it, because that's where the magic happens. And what we also found is very important is to use a data format that the revision control system can merge. Because at a demo party, when you are drunkenly coding and working on stuff together and working at the same thing together, and your revision control system just merges it, is much better than going outside for a fight. So ASCII data formats are really important. Then a general tip for the process is to create lots of bad releases. Sir Garbage Truck, please. It's much better to create lots of bad releases than to try to create one good one, because then your tools are tested. The Epsilon thing taught us that if you only start to use your tool the first time when you do your big release with it, you will suffer quite a bit. Whereas just doing very, very bad entries on purpose allows you to find all the bugs in your code beforehand. So that might require you to have some fake groups and fake identities. But eventually it might happen that the fake identities are actually more popular. At least some people seem to like Saxaline a lot. It was supposed to be one of my fake identities to release bad stuff, but I suppose it's no longer. And then please make sure that identical code runs in your editor and your intro builds, because if you do not, then your wonderful release that you just finished will not work properly on the compo machine, and you will spend a lot of time suffering. So it makes sense to write your render code as a module, as a library, or whatever your language supports, and just have the editor feed data into it, because otherwise you will suffer. Visuals and colors. One thing that we found works really, really well is don't let the same person build a scene and choose its colors. Because, at least for us, the people who are good with building geometry are horrible with colors. And also, if you have an idea what the scene is supposed to be and you build it like that, it's probably okay. But here, the misunderstanding, once again, misunderstanding as a creative process once again comes into play. You build a scene, you make all colors configurable, you set them to gray, and let another person choose it, and it's normally 100% better. Further on, color grading allows you to choose look and materials independently. Normally, if you just if you just render, you choose a color and that's the color. But especially if you're going in the direction of physically based shading, you might want to actually consider what is the material I'm rendering, and if you want it to be stone, you can make it look like stone, and it can be any color, and afterwards color grading allows you to just make it look smooth or not smooth or dangerous or threatening or friendly, and you no longer have to create the content thinking of what it is supposed to look like, but just what it's supposed to be. And then in terms of colors and demo parties, it's very important for you to know what your projector displays and what it does not. We have this beam slide that I'm not sure if it's being shown here. It's available at that URL, mercury.sexy/calibration02.png. If you manage to convince organizers to show this on the big screen, you are able to read what the projector can do and cannot do. So there's the black squares on the left, and you can simply look at what is the lowest number, the darkest color you can still see, and then make sure that you do not use any colors darker than that in your release. And the same is on the right, the white saturation, what is the highest color. And in between there's these gamma ramps, and you can try to see where the point is that the black and white stipple and the gray gradient has the same color value, and that gives you the gamma value. And then your release will actually look like what you want it to look like from your monitor, because if you are not working projector aware, you will most likely choose too dark colors and will not be visible on the big screen. Okay, and with these random hints, I come to the end, and I hope you got some nice ideas on how to make things. Some of these are applicable for other sizes than 64K. Some of them are applicable for daily life as well. Maybe misunderstanding code is a good idea also in production environments. I have no idea, because I also actually have no idea what I'm doing. And it continues to amaze me how with every generation of tool we're writing, we are basically slapping our foreheads why we didn't think of this beforehand. So it might be that there will be a talk eventually in some assembly in the future. Well, I'll tell you that everything I told you is wrong, but the important part is to make bad stuff early and often. So please do that. And then once you've done bad stuff, do some good stuff in between. I certainly shall try that. Thanks. I think people can ask questions. Good question. The question was, how do we include music? Because I haven't talked about that at all, because I have only written the graphics part of it. So there are a number of approaches you can do this. One is to use the internet and search for available synthesizers for 64K. Unfortunately, the only one that's really openly available is the V2 synthesizer by Farbrausch, which is 15 years old and has the problem that if you use it in your demo and Cabby, who wrote it, is present in the party, he will stand up and shout the preset names at you, because he has heard it so often from every release that he can't stand it anymore. The other option, I mean, there's other ones for 4K. There's Vorklang, and then there's Sinter, I think. Klingster, yes. But if you do not want to download something, if you want to understand what you're doing, which I encourage, you have to write a small software synthesizer. You have to start by creating some waveforms and making music with it, which is difficult, which I've tried, and everything I've ever done with it sounded horrible. And I'm actually quite happy that Red of Mercury has written a synth that fits in 64K, that he and only he can use, and that produces good music. But I unfortunately cannot give you any good practical hints on how to do it, because I have not figured that out either.
Any other questions?
Seems not. Or is there? Ah, there's one. How we go, what? Yeah. Well, that precise file there that creates the node system is about 5,000 lines long, but the entire source base source code, I think it's about 80,000 lines of code, including the graphical user interface. Of course, at least 3/4 of that is graphical user interface boilerplate code, which everybody hated to write and nobody really wants to look at ever again. But basically none of that is auto-generated. It's all written by hand, and it was very, very horrible, and it took quite a while. Oh, the compile data, I actually don't know how many lines that is, because the data gets exported into a header file, and when I try to open the header file, Visual Studio died. So it's very long. The advantage of having always repeating data means that it packs well, but if you have 30,000 lines of zeros in your file, that packs to about 4 bytes in the final binary. So we are not shy of putting 30,000 zeros in this file, which means that it has many hundreds of thousands of lines of zero data, and it's impossible to look at it. For tiny test problems, debugging the initial exporter and importer, that worked still. That was small, and I looked at it by hand. But nowadays, for an actual release, I have no idea how big they are. They're huge, but the only relevant quantity is how big the final binary are, and as long as it's small enough, then it goes. With some compiler, I think we ran into a size limit of an array can only have 1 million entries or something.
Anyone else?
How long does it take to make something like paradox?
The question is, how long does it take to make something like Fermi Paradox? So I showed this frame. What was the key here? I showed this example of the City of the Timeless in its first version. Where was it? Very far in the front. With the untweaked bar. Here. This was about 3 years before it was released. We first had the idea that we want to make it 64K about architecture. And we built this. And we thought we can't make a demo around this. It doesn't work. And we abandoned it. And then we did other things. And then a year later, we looked at it again, and we built some other parts of it. And then we abandoned it again. And then finally, we decided that we could actually, we have this other thing lying around, and oh, we have this as well, and then we assemble it together. So it's a very long process, but it's not a continuous process. The idea of making something with space has also been around for a very long time. And for example, the planet rendering was, I think, at Payback 2015. We already did a shitty demo with some stars and planets and spaceships, and some of that code has gone into Fermi Paradox at the end. But in the end, the final push to actually making it, I mean, normally the awesome 64Ks are released at revision, or it was the case until now, because no assembly has the 64K into compo. So we normally started around more or less directly after Christmas to see what we can do. And seeing what we can do means, in our case, that every Sunday we just, in our version control system, everybody pushes something in the every week's directory, and we look at what the others did. And then we comment on each other and criticize it. And we do this every week, and we have been doing this every week for 120 weeks now. So everybody does a little bit something every week, and then we just push it together, and whatever is there is there. And then we come to the party, and our timeline is empty, and we are basically panicking and shouting at each other that we should have started much earlier again. And it turns out okay at the end. We're never relying on it to turn out okay, but so far it seems to have worked.
We have time for one question. If you don't have any questions, thank you.
All right. Thank you for being here.